Let's consider how to incorporate technology in our calculation of binomial distribution probabilities. There are three main parameters that come with a binomial distribution. X, which is our number of successes, N, which is our number of trials, and P, which is our probability of success for each trial. So in this expression for the Excel or Google function, binom.dist, number S is X, our number of successes, trials is N, probability of a success is P. This last argument, cumulative, comes as either true or false. So you will type the word true or the word false as the last argument to this function. In looking at the description for cumulative, this function binom.dist actually is two different types of functions. If the cumulative is listed as true, we'll take the probability of 0 successes plus the probability of 1 success all the way up to the probability of X successes. Cumulative meaning we're adding up all of the ones before. So if cumulative is true, we add up all the ones before. If cumulative is false, it only returns the probability of X successes. So that's really the difference between them. We would use the true in the cumulative if we were trying to determine the probability of some number of successes or less. So an example would be X is less than or equal to 5. We would add up 0, 1, 2, 3, 4, and 5 to get that probability. Whereas if we just said X equals 5, we only get the probability of 5. It takes practice in looking at which type of situation we're covering. So we'll be practicing. As for this combination, this is just a reminder that this is our NCR function. We're not going to be using this a lot. So you could probably just gently cross it out. If we're going to do a binomial distribution, we'll just use the function in its whole. In regards to the words success versus failure in a binomial distribution, don't let the words confuse you. Success is intended to refer to the desired outcome, whatever the desired outcome is. Failure would be not getting the desired outcome. Remember that if we want to determine whether a probability distribution is a binomial distribution, we have to check all 4 requirements. So that quiz that we took at the beginning, let's walk through them. Each trial can have only 2 possible outcomes, success or failure. For the quiz, we had a correct answer and an incorrect answers. There must be a fixed number of trials. We had 5 questions on the quiz, a fixed number. It cannot go on forever and ever and ever. There has to be an ending. The outcomes for each trial must be independent of each other. In the quiz, this is that the answer for one question does not change the probability of getting the other questions correct. And then the last one, the probability of success must remain the same for each trial. And here we had 1 correct answer out of 4 possible answers. So we kept that 1/4 probability for every single question. If even one of the requirements above is not met, then we do not call that probability distribution a binomial distribution. So this example 1, we actually already calculated this in the previous part of the lesson. Sorry about that. I don't want you to use techniques from chapter 4. Instead, use the binomial formula by hand. Find the probability of getting exactly 3 questions correct on the quiz. I'll let you review that one. Plug in your answer. Probability of exactly 3 will be 0.088. And again, that's something that we just did earlier. I want to look at example 2 and pull in technology. So example 2 is actually asking us to use the formula to calculate the probability of getting none correct, exactly 1, 2, 3, 4 correct, or all 5 correct. So we're going to basically create our probability distribution table in technology. Okay, and for the past few videos I've been using Google. This time I'll use Excel just to mix it up. Process is going to be the same. I'm working on example 2 to use the formula to calculate the probabilities. I like using cell references, so we're going to use cell references. We'll put N and P here. So N, we had 5 questions, 5 total trials, and P, the probability, was 0.25 or 1/4. Remember, if you want to put the fraction in, you need to force the technology to calculate. So you'll type in equals 1 divided by 4. You don't just want to put 1/4 in there. The technology will not calculate that as 1/4. So force it to make it a decimal. And then we'll create our probability distribution. I'm going to put x here and p of x here so that I can create a table. And I'm just going to make it a little bit neater, give it some borders, maybe put everything nice and neat in the center. For x values, I have none correct, 1 correct, 2, 3, 4, or all 5 correct. And then for p of x, in order to calculate p of x, we'll start in the first square. And remember, I'm using cell references, so let's talk through how to do that. Binom.dist, parentheses. Our first value should be number s. This is the number of successes, which is given by x. That's my x. The next value is n, and n is 5, comma. The next value is p, so I'll click on that, comma. And then notice it gives me true or false. True is a cumulative distribution, meaning we're adding up all those that come below as well. And then false is just that value. So the probability mass function that's written there, it just means that one value is all we're going to calculate the probability for. Since our example is asking us for each of these values, we're going to do false for just that value. Type it in and we get 0.237 for our probability. Now I could drag it down, but I'm going to have a problem if I try to drag it down. Because B1 and B2 are not locked, when I drag this formula down, those values will change. When I drag a formula down, it changes the cell references based on the location as I drag it. So I want to lock B1, I'm going to put $signs around it, and B2. So I'll put $signs around the B for each of those, for the N and the P. I want those to stay always in this group. And then, in order to get the other values, instead of typing this 5 more times, I'm going to make sure that my mouse has changed to the plus sign, grab the handle, hold down my mouse button, drag all the way down to 5. And it's automatically changing the X value. Notice that A5 there, A6, A7. So every single time I'm clicking into a new one, it's only moving the X, not the N and the P. And oh, I accidentally clicked off of it while I was in the formula. Just hit escape to go back. And here are our probabilities. Number of decimal places, it's up to you. Usually we like 3 or 4 decimal places, so here we have 4. 3 or 4 should be sufficient. We want at least 3 decimal places. And there we have using technology. Let's look back and see what else we could do. We can use the binomial distribution to answer more complicated questions like, what's the probability of answering either 2 or 4 questions correctly? What's the probability of answering at least 3 questions correctly? What's the probability of answering at least 1 question correctly? Writing these out in notation, this would be probability that x equals 2 plus probability x equals 4. So we would just take the 2 and the 4 probabilities and add them up. At least 3 would be x equals 3, x equals 4, x equals 5 for the probabilities. Or we could write that a little more succinctly, x greater than or equal to 3. And at least 1 question correctly, this would be probability of 1 plus 2, all the way up to probability of 5. Or 1 minus probability of 0, because that's the only case that we leave out. We can do this pretty easily in our technology. So for a probability of 2 or 4, I would look at the probability of 2 and click on it, add the probability of 4, click on it, 0.278. Probability of at least 3, you could do this in several different ways, but I'm going to take the sum of 3, 4, and 5. At least means 3 is the smallest, 3 is the least, 0.1035. At least 1, both of these are quick in technology. We could either do sum of at 1 through 5, or we could do 1 minus the probability of 0, and we get the same value. So calculating different combinations of getting questions right. If we have our probability distribution table, it's pretty easy to grab the values and add them up, especially in technologies. And notice for 2 or 4, we're not double counting any events. These are mutually exclusive. So we're able to just take probability of 2 plus probability of 4. And then if you flip your page, we can fill these answers in quickly for those values. In the next part of our lesson, we'll talk about the mean, the variance, and the standard deviation specifically for a binomial distribution. It actually turns out that even though a binomial distribution is just another discrete probability distribution, because of the way that it's structured, the mean, the variance, and the standard deviation formulas simplify greatly into some nice formulaic calculations. And all we need to know are the values of n and p in order to calculate them.